Hi and welcome everyone. In this video, I want to go over problem number 9, section 2.4. And this is a very good and detailed problem that in each part explains the equation of planes and orthogonal planes and so on. And this is going to help you solve the other problems. So let's solve this step by step. So let's see what it says. Orthogonal planes, we will define two planes pi1 and pi2 in R3 to be orthogonal to each other if any normal vector to pi1 is orthogonal to any normal vector to pi2. Be patient, I'll go over this with the example. Part A, show that the two planes pi1 3x minus 5y plus 2z equals to 6 and pi2 2x plus 4y plus 7z equals to minus 3 are orthogonal to each other. Let's go over this part first. Now I put a note here for you. Two vectors are orthogonal or perpendicular. We know that now if their dot product is 0. So u is perpendicular to v or orthogonal to v if and only if u dot v equals to 0. So when we have two planes, plane 1 has a normal vector, which is orthogonal to the plane itself. So this is pi1, and we have pi2, and this is the normal vector for pi2. And then we clearly see if the planes are orthogonal to each other, then the normal vectors are orthogonal to each other. So if we want to show two planes are orthogonal, what we can do is take the dot product of the components of the normal vectors, and if that's 0, that means they are going to be orthogonal. So the plane 1, the components of the normal vector for the plane 1 are the coefficients here. So 3, negative 5, 2, and same for pi2 and the plane 2, we have 2, 4, and 7, 2, 4, and 7. Let's take the dot product of these two vectors, and when we take the dot product, we already know you take the first component of the first vector times the first component of the second vector plus the second component of the first vector times the second component of the second vector and plus the third component of the first vector times the third component of the second vector. And if you do that, you do get 0, so the planes are orthogonal. Two planes are orthogonal if their normal vectors are orthogonal to each other. I wrote it here again. So let's see what the next part says. Find a vector equation for the line of intersection. Now, if you notice, this is an equation and that's an equation. So if you want to know where these two equations intersect each other, you can just solve the system, and that's what I did. So you write the system, you put the two equations of the planes, and you can write the augmented matrix and then do the RREF. And here it was short. You can use technology if you want to. So, but I did it just to review the row operation. So first, I wanted to make that one. You can divide by 3, or you can just say negative R2 plus R1. That becomes 1, that becomes negative 9, that becomes negative 5, and that becomes 9. So, and you know that R2 doesn't change. Now we want to make that 0, so we can do negative 2R1 plus R2. Negative 2 times 1 is negative 2 plus 2 is 0, and so on. Negative 2 times negative 9 is 18 plus 4 is 22. Negative 2 times negative 5 is positive 10 plus 7 is 17. And so on. Negative 2 times 9 is negative 18 minus 3 is negative 21. Then you want to make that 1, so you can divide R2 by 22. And if you do that, R1 doesn't change. So you get 0, 1, 17 over 22, negative 21 over 22. One more step left. We want to make that 0. So we can just do 9 times that, or 9 times this row plus the first row, and I wrote that here, so let's put that, change that to R1, and if you do that, again, this doesn't change, negative 9 times 1 minus 9 is 0. 9 times 17 over 22 minus 5. And if you do the calculations, I wrote it here for you, you do get 43 over 22. And finally, 9 times negative 21 over 22 plus 9. So I did 9 times negative 21 over 22 plus 9. To do it fast, I factored out 9. So you get negative 21 over 22 plus 1. That's negative 21 over 20 plus 22 over 22. And finally, you get 9 over 22. You know, this is your x, this is your y, and that's your z. Here we have z. This is a non-pivot column, so z is the free variable. That's how I called it. Then you can rewrite the system x plus 43 over 22 z equals to 9 over 22 y plus 17. I'm right here. 22z is negative 21 over 22. Then you can isolate x, and instead of z, you can substitute t. So what's going to happen, you're going to get x is 9 over 12 minus 43 over 22t. Y is negative 21 over 22 minus 17 over 22t. And z equals just t. So now if you can write x, y, z, these are the coordinates of the point. And here it's 0. And then plus, you can factor out t over 22. And you're going to get negative 43, 17, negative 17, 22. So if you just have this, that's a good answer. These are the parametric equations of the line. Part B of the problem, it says find a Cartesian equation of plane P3 or pi3 that contains the line with that equation and is also orthogonal to the plane 1, pi 1, 3x minus 5y plus 2z equals to 6. Now to find the plane, we need the coordinates of the point. And this point, this line is on the plane, so we can just take those points. These are the coordinates of a point on the plane, 2, 5, negative 7. Now line 1, if we separate them, can be written as 2, 5, negative 7 plus t times 1, negative 3, and 1. And I call that vector. This is the direction vector of the line. The components 1, negative 3, and 1. So let's see what happens here. So we have our L, the line, and with that vector, which is 1, negative 3, and 1, then we have our N1. So basically what we want to find is that. So the coordinates of the components of N3, and I don't know what they are. We don't know. We have to find them, and that's ABC. So, and also we know we have a point on this plane, and pi 3, which is kind of, this is our plane pi 3, which the coordinates of that point are 2, 5, negative 7. So how can we find this? So we know that this vector N3 is perpendicular or orthogonal to this, to U. So U, vector U dot N3 should be equal to 0. And we don't know what the components are, so you can just put A, B, C. So you get the first equation, which is A minus 3 plus equals to 0. And you know that N1 is also perpendicular to N3. So if you do N3 dot N1, which is 3, negative 5, and 2 dot ABC again, will give you 0. And if you want to find the equation of this plane, we can just use the equation of a plane, the standard form, and we have the coordinates of this point. Those point x0, y0, and z0. I'll show you what they are now. It's right here, this, but what we need to find is ABC. So what we can do is solve this system again for ABC. Now, if you write the augmented matrix, this is like a homogeneous equation. So the homogeneous system, you can do the RREF, and if you do that, you get an interesting answer. So we get first 1, 0, 1 over 4, and you get 0, and here you get 0, 1, negative 1 over 4, and 0. So you know this is your A, your B, and your C. If you write it back, we know from the first equation A plus 1 over 4C is 0, and B minus 1 over 4C is also 0. A equals to negative 1 over 4C, and B equals to 1 over 4C. So we can see, you can say C is negative 4A and C is negative 4B, and we know that A equals to negative B. So basically any number we take, the easiest number we can take, if we say A is 1, then B is going to be negative 1, and C is going to be, if you substitute, negative 4, and any scalar multiple to the A, B, C are going to be the components of the vector n3. So you kind of, if you take 2 here, you get negative 2, and here you get negative 8, and so on. So we do have the components. We can just pick the simplest one. So you can say 1 times x minus 2 minus 1 times y minus 5 minus 4 times z plus 7 equals to 0. And if you simplify, you get x minus 5 plus 4 z minus 25 equals to 0. Or x minus 5 minus 4 is equals to 25, or negative x plus 5 plus 4 is equals to negative 25. So both answers are good. There may be other ways of doing this, but I think since we're talking about orthogonality, so dot product is the best way to proceed. Now, part C says, suppose pi 1, the first plane with that equation. So, and just the same thing as the above, show that A1, A, the point 3, 1, 1, and B, the point 5, 1, negative 1 are both on pi 1. If you want to show that, all you have to do is substitute these values for x, y, z in the equation of the plane, and you have to get both sides to be equal to each other. If you do that, these are pretty simple calculations. So you get 6 equals to 6, same as for point B. So it will work. Now, next part, it says, then find Cartesian equation for a plane pi 4 that contains AB, contains these 2 points again. So both planes share those points because A contains that, pi 1 contains that, and pi 4 that we want to calculate or find the equation also contains these 2 points. So AB such that pi 4 is, but then these 2 planes, pi 4 and pi 1, are orthogonal to each other. So let's see how we can proceed. Now, the way I did it, I know this is my pi 1, and this is the normal vector. We have the components of that vector. We want to find the components of this vector n, which is the normal of pi 4. But we know we have point A and B. I didn't put the coordinates, you already have the coordinates, but you can find the vector of those that connects these 2 points, so which is vector AB. Now, how you find that? Just finding the components of a vector passing through 2 points. So it's 5 minus 3, 1 minus 1, and negative 2 minus 1. You just subtract the coordinates. So we have that vector, and that vector, if I bring it up here, you know that vector cross that vector is going to give you an orthogonal vector to both of them. So one more time, if I bring this AB up, which we can do parallel, they're parallel, so we can do it. We have that if you do the cross product of these 2 vectors, which is vector AB and N1, you get a vector that is perpendicular to both vectors, and that's going to be parallel to N, and we can use those components. So the cross product, again, I know by now you know how to do the cross product. So you write the components of the first vector, u, 2, 0, negative 3, and the components of n1 are 3, minus 5, and 2. And again, the I component, you just hide that, and it's the determinant of that matrix, which is 0 times 2 minus negative 3 times negative 5. So that's the I component. For J component, you hide so the row with J and the column with J. So 2, 3, 3, 2, and you find the determinant of that. So it's minus for J always 2 times 2 minus negative 3 times 3, 2 times 2 minus negative 3 times 3. And the K component, we hide that and that, and you take the determinant of that. So it's 2 times negative 5 and minus 0 times 3. And this is what you get. Now, this we need the coordinates of a point. That point can be either A or B. I picked A, and you use this component. So it's negative 15 times x minus 3 plus 13 times y minus 2 and minus 10 times z minus 1, and that's 0. You simplify and you get that, or you can change the signs. Both answers are perfect. Part D, it says follow up to C, find a vector equation for the line L containing AB in part C, and check that every point x, y, z on L satisfy the equation pi 1 and pi 4. Now the vector direction, so we had 2 points A and B. The vector direction of that line that we want to find is just the vector components of the vector connecting A to B, and we found that. So let me just go up there and show it to you. It's right here. So we have the components of that vector, and or you can just write negative 2, 0, 3, doesn't make any difference. The line x, y, z, it's a line you pick again 1 point plus t times the component of the direction vector. And if you do that for x, you get 3 plus 2t or 3 minus 2t, doesn't make any difference. Y is going to be 1, and that number plus 0, and z is going to be 1 plus 3t. Now to check if they share that line, what you can do is take x, y, and z and substitute in pi 1 in the equation of the pi 1 and in the equation of the pi 4, and both sides, for both sides you have to get the same thing, and try that. You will get the right answer. I think that's it for this recording or for this video, and please watch this 2-3 times, and that will help you to do the next problems. Remember, to find the equation of a plane, you need the coordinates of a line and the components of vector n of the plane. For the equation of a line in 3D, you need the components of the direction vector of that line and a point on the line. Once you can find what these are, then you can solve every single problem. For some of them, you can think about it, and find those components and the coordinates of those points. Thank you for watching, and I'll see you in my next video. Have a good one.